Welcome to this Ford technical training program on the essentials of drivability diagnosis. This program is designed to demonstrate the correct way to diagnose and service vehicle drivability concerns. This program is divided into 5 lessons. At the end of each lesson, you'll be asked to return to your accompanying workbooks to complete the progress check for that lesson. Lesson 1, Diagnosis. As you know, communication between the customer, service writer, and you, the technician, is essential. Communication requires consistent use of terminology to prevent misunderstandings. To prevent misunderstandings in this course, we'll use the following standard terms. Concern, the customer's reason for bringing the vehicle in for diagnosis. The customer perceives or worries that something may be wrong with the vehicle. Symptom, an identifiable display of abnormal operation expressed in standard terminology. Condition, the circumstances or factors of abnormal operation. And cause, the component or system whose abnormal operation creates the condition. For example, a customer brings a vehicle in because of a concern about noise from the engine. In this case, the symptom for the noise is spark knock, detonation. The condition is an overheated engine, and the cause is an inoperative cooling fan. The first step in diagnosing a problem is identifying the symptom. The following are some examples of common symptoms you may encounter along with their definitions. Engine misses is defined as vibration caused by one or more cylinders consistently failing to produce power. Engine runs rough is defined as vibration caused by inconsistent production of power. Sometimes the difference between symptoms can be subtle. Let's compare the sound of an engine missing with the sound of an engine running rough so you can hear the difference. This is engine missing. This is engine running rough. Engine missing and engine running rough. Now, let's take a look at the difference between an engine stalling and an engine quitting. Engine stalls is defined as engine stops running under load. This usually occurs at idle when a transmission gear is engaged. However, the engine will readily restart. While engine quits is defined as the engine stops running for no apparent reason. But again, the engine will readily restart. Dieseling is defined as engine continues to run after the key is turned to the off position, but now runs very roughly. Engine surge is defined as engine speed changes while throttle position remains steady. Now, let's compare hesitation to stumble. Hesitation is defined as a lag occurs between the time the accelerator is lightly pushed, tipped in, and acceleration begins. Stumble is slightly different and is defined as a drop-off of power between the time the throttle is opened more and speed increases. Buck jerk and trailer hitching are another pair of similar symptoms. Buck jerk is defined as a sudden lurch due to power flow interruption during acceleration. Trailer hitching differs from buck jerk in that it is a sudden lurch that occurs due to power flow interruption during deceleration. Rolling idle is defined as engine speed varies frequently during idle. High idle speed and slow to return to idle are two more symptoms that are similar enough to sometimes make them difficult to differentiate. High idle speed is defined as idle speed is faster than specification, while slow to return to idle is defined as engine speed remains high too long when the throttle is returned to the idle position. Now that you've taken the first step in determining the problem by identifying the symptom, you're ready for diagnosis. Diagnosis is a careful examination of the symptoms in an attempt to identify the condition. Accurate diagnosis is only possible when you understand and apply the relationships between symptoms and their causes. A systematic process is required to relate the symptom to the cause. There are 9 steps to this process. 1. Verify the symptom. 2. Identify the condition. 3. Identify related symptoms. 4. Identify the systems. 5. Perform diagnostic tests. 6. Interpret test results. 7. Isolate the root cause. 8. Repair the problem. And 9. Verify the repair. Let's look at each of these steps in detail. Experience the symptom for yourself. If you only go by what someone tells you, you may not have a complete or accurate description. There could be misunderstandings due to differences in terminology, or the symptom may be caused by driving techniques or circumstances that you might not encounter on a typical test drive. For example, if the driver complains of lack of power from a car with a manual transmission, you would want to verify that the driver knows which gear to select for the circumstances. The best situation is for the driver to demonstrate the symptom to you. If that's not practical, try to obtain information about the circumstances when the symptom occurs. This will enable you to duplicate the circumstances. For example, if the driver says that the symptom only occurs while driving uphill, you would want to conduct a test drive including hills. A quick and accurate diagnosis is only possible when you have knowledge of symptoms and their causes. Use your knowledge about relationships between symptoms and conditions to determine what are the possible causes of the symptom. More than one problem may be causing the symptom. Remember to consider all possible causes of every symptom. For example, lack of power is usually associated with air-fuel ratio, ignition timing, engine compression pressures, and gear ratios. Limit your evaluation to the likely conditions. For example, you would not bother with the drive shaft. More than one symptom may be caused by the same problem. Ask about other symptoms that may not have been mentioned, which could be caused by the same conditions that cause the primary symptom. For example, the conditions that cause lack of power can also cause other symptoms, such as engine misses, engine runs rough, poor fuel economy, induction backfire, exhaust backfire, spark knock, exhaust smoke, stumble, and hard starting. If other symptoms exist, then identify the conditions that each of the symptoms have in common. For example, you discover that the vehicle also has these symptoms: engine runs rough, engine misses, hard starting, and exhaust smoke. Ask yourself what conditions the multiple symptoms have in common. Refer to the PCED shop manual for additional symptoms. By identifying other symptoms and relating the conditions that cause the symptoms, you rule out a number of conditions. For example, there are only 2 likely conditions that the symptoms have in common: air-fuel ratio and engine compression. There's no need to spend time on gear ratios and ignition timing. Of course, a vehicle can have more than one malfunction at a time, so multiple symptoms can be from unrelated conditions. Use your skills and knowledge to recognize the relationships between symptoms and conditions. Select the most likely causes from the list of possible causes in the PCED manual and from your own knowledge and experience. Think about the differences in symptoms that can be caused by the different systems. This will help you select the most likely causes. If causes are equally likely, then use cost factors to prioritize the systems that you'll check first. Cost depends on time and materials. Time is usually the basis for decisions about the sequence of tests. First, test the systems that can be tested quickly. Consider the possibility that more than one system can be tested with the same equipment hookup or amount of disassembly. Group these systems together when deciding how much time each set of tests will take. Prioritize tests depending on the potential costs of extra time and materials that could likely be incurred because of accidental damage during disassembly and reassembly. Performing tests on a system will identify whether the system is the cause for the symptom. Use the directions in the service manual for the vehicle. Select the tools and diagnostic equipment for the test. If diagnostic equipment is used, follow the directions for its use. For example, exhaust gases are analyzed and cylinder compression is tested. Refer to the service manuals for the vehicle for the specifications and description of normal operation of the system being tested. Compare the test results to the specifications. For example, engine compression pressure is lower than specifications in several cylinders. The specific malfunction in the system must be identified. For example, you must identify why compression pressures are low. This will enable you to identify whether the problem is the piston rings, valves, head gaskets, a cracked cylinder head, or the engine block. Further testing may be required to identify the specific component that needs to be repaired. For example, you use a cylinder leak-down test to isolate the root cause. The test results indicate that the piston rings are leaking excessively. It is very important to identify the cause of unusual wear or damage to parts. Examining related components is a good place to start. For example, let's say that you disassembled the engine and discovered that the piston rings, pistons, and cylinders were scored and blue-black in color. Think about what would cause unusual wear or damage. For example, the likely cause is an occasion of engine overheating. Investigate to find out if the driver experienced a situation that may have caused the damage, or look for physical evidence of damage. For example, ask if the driver experienced an incident of engine overheating. Let's say the answer is yes. If a previous situation occurred, ask if the problem was successfully identified and repaired. Your investigation may discover that there is another problem to be repaired. For example, ask what was done to the cooling system, and if the engine overheated after the repair. Let's say that the thermostat was recently replaced, and the driver did not notice overheating thereafter. Whether the previous problem was repaired or not, you should be alert for evidence that the problem may still exist. Otherwise, you risk damage that could reoccur after you've made your repairs. Even if the cause of the previous problem was repaired, you should consider that other parts may have been damaged. For example, inspect for a warped or cracked engine block or cylinder heads. It's also possible that the previous repair was done improperly or was a misdiagnosis. Look for evidence of causes of the initial problem. For example, let's say you find that the engine cooling fan is inoperative. Use your skills and knowledge and the recommended procedures for making the repair. After repairs have been completed, test the vehicle for the original symptom or symptoms. Be alert for new symptoms because mistakes can happen during repairs or new problems can develop. Be especially alert for conditions that may have caused the initial problem. For example, you should carefully monitor engine temperature and operation of the cooling system. Diagnosis and repair is much quicker and more accurate if a logical thought process is used. It's mind over matter. Spend a few moments thinking the problem through, rather than hours of unnecessary tests and disassembly reassembly. This is the end of Lesson 1. Please stop the tape, then return to your workbook and complete the progress check questions for this lesson. Lesson 2, Engine Requirements and Operating Modes. Engines are designed to provide good drivability, maximum power and economy, with the least amount of emissions. Engines must perform well in 5 different major modes, starting idle, acceleration, high load, cruise, and deceleration. In each of these modes, the engine has different requirements. This course will help you understand the requirements of the engine to perform properly in each mode. There are 3 basic requirements for an automobile engine to run: a combustible air-fuel mixture, compression to compact the air-fuel mixture so that it will produce usable power when it burns and expands, and a spark to ignite the compacted air-fuel mixture. These requirements vary depending on the operation mode and conditions. Ignition and air-fuel will be covered in detail in later engine performance curriculum courses. Knowledge of the requirements of the engine during operating modes will enable you to relate symptoms to abnormal conditions. A drivability symptom caused by the engine will not exist if all requirements of the engine are being met for the operating conditions. Let's look at what happens in the engine during the idle and acceleration modes. Very little power is required to keep the engine running at idle. The engine only needs to produce enough power to carry the accessory loads. Accessory loads include the power steering pump, AC compressor, generator, and the automatic transmission when it's engaged. Normal idle speed is typically between 720 and 780 RPM for a 4-cylinder engine. Stalling may occur if idle speed is abnormally low because not enough power is produced to carry the loads. Stalling is especially likely when an additional load is applied, such as engaging the automatic transmission, turning on air conditioning, or using power steering. Manifold vacuum is very high during the intake stroke, typically 17 to 20 inches of vacuum for a 4-cylinder engine. This is because the throttle plate that regulates how much air can flow into the engine is nearly closed. However, the pistons are moving fast enough to draw in more air than can flow past the throttle plate, creating a vacuum in the intake manifold. High vacuum means that there is very little pressure to push the air-fuel mixture into the cylinders. Thus, very little air-fuel mixture enters the cylinder on the intake stroke. In addition, intake air volume is low. This is because engine speed is relatively low, and the throttle plate is nearly closed. And because engine speed is relatively low, intake air velocity is also low. During the compression stroke, compression pressure is low. This is because the manifold vacuum is high. High vacuum always causes low compression pressure. This is because there is less pressure in the intake manifold, so less air is pushed into the cylinders during the intake stroke. And because compression pressure is low, compression temperature is also low. During the combustion stroke, very little power is produced. The amount of power produced is directly related to the amount of pressure created by the expansion of the air-fuel mixture when it burns and gets hotter. During idle, there is very little combustion pressure, and because compression pressure is low, combustion temperature is low. During idle, exhaust pressure and temperature are low. This is because combustion pressure and temperature are low. The amount of exhaust gases depends upon the volume of air-fuel mixture that entered the cylinder during the intake stroke. During idle, very little air-fuel mixture enters the cylinder to begin with, so very little burned gases will be expelled from the cylinder. Exhaust back pressure is also low. This is because the intake air volume is low and exhaust pressure is low. The amount of back pressure in the exhaust system depends upon the volume of exhaust that is being expelled from the cylinder. There are 2 factors governing this. 1, the volume of exhaust gases in the cylinder, and 2, the number of exhaust strokes per minute, engine RPM. During idle, the volume of exhaust gases in the cylinder is small following each combustion, and the number of exhaust strokes per minute is also small because the engine is turning very few RPM. Now, let's examine what occurs in the engine during the acceleration mode with a high engine load. High engine loads occur during conditions such as acceleration, extreme high-speed driving, trailer towing, strong headwinds, and climbing hills. Acceleration requires much more power than maintaining a steady speed. The conditions shown are based on the highest possible load. The throttle plate is wide open. Engine speed is high, 3,000 to 5,500 RPM. This will provide the best contrast for an engine producing maximum power. During acceleration, manifold vacuum is low, typically 0 to 5 inches of vacuum. This is because the throttle is wide open. The throttle plate wider allows more air to flow. The speed of the pistons determines how much air could flow into the engine if the throttle was not restricting the airflow. During acceleration, the pistons are moving very fast, so the volume and velocity of intake air is very high. With no restriction to the amount of air that can enter the intake, vacuum is very low. A rich air-fuel mixture is used. This is because the extra fuel produces maximum power. The amount of air-fuel mixture that enters the cylinder depends upon how much is available in the intake path. During acceleration, there's an unlimited amount of air-fuel mixture in the intake path, so the cylinder fills to capacity. During the compression stroke, compression pressure and temperature are very high. This is because manifold vacuum is very low. The amount of pressure depends on the volume of air-fuel mixture that's being compacted into the combustion chamber. During acceleration, there's a lot of pressure because a lot of air-fuel mixture is compacted into a much smaller space. Combustion pressure is very high during the combustion or power stroke for two reasons. One, compression pressure is very high during acceleration. And two, a rich air-fuel mixture is being burned. These factors provide greater expansion during combustion. Therefore, maximum power is produced. During acceleration, exhaust pressure is very high because combustion pressure is very high. The pistons are moving very fast to push the exhaust out. Since a lot of air-fuel mixture entered the cylinder to begin with, there are a lot of burned gases that have to be expelled from the cylinder. Exhaust temperature is moderate because combustion temperature is moderate at this point. But exhaust back pressure is high. This is because intake air volume is at its maximum during acceleration, and exhaust pressure is very high due to the large volume of exhaust gases in the cylinder following each combustion. RPM is high, so there are many exhaust strokes per minute. In addition to becoming familiar with the normal operation of the engine, it's a good idea to also familiarize yourself with some of the abnormal conditions you may encounter. During idle mode, the engine produces just enough power to keep itself running. Additional loads may cause the engine to stall if the engine is not producing enough power to handle the additional loads, as would be the case if the engine is idling too slow. A restricted exhaust system causes loss of power. Some of the exhaust remains in the combustion chamber, replacing a portion of the air-fuel mixture. In the description of different operating modes, you learned how the relationship between RPM and throttle opening determines the airflow volume and velocity during the intake strokes. And you learned how the volume of air in the cylinder determines the pressures and temperatures during compression, combustion, and exhaust strokes. However, other factors affect the amount of power that can be produced by the air-fuel mixture. Air temperature and barometric pressure are factors outside the engine that affect its power. The temperature of the intake air affects power. Warmer air is not as dense because it is expanded from being heated. Therefore, it contains less oxygen for the burning process. Also, air that has already expanded will produce less expansion during the burning process. Therefore, warmer air produces less power. The density of the intake air affects power. When the barometric pressure is lower, there is less pressure to push it into the engine's intake. The other aspect of lower barometric pressure is that the air is less dense. Therefore, it contains less oxygen for the burning process. Also, air that is less dense will expand less during the burning process, and therefore produces less power. You hear about changes in barometric pressure in the daily weather reports. However, the slight changes caused by weather are much less important than the large differences in barometric pressure that occur with changes in altitude. Barometric pressure is much lower at higher altitudes than it is at sea level. Since an automobile may be driven between places with different altitudes, its engine will operate in different conditions. In some areas, a relatively short drive can be over terrain that will be at widely varying altitudes. For example, in some places, you can drive from sea level to the top of a mountain 10,000 feet high in less than an hour. There is much lower pressure and less oxygen in the air at 10,000 feet. Yet the driver wants the car to perform well in any location. Furthermore, the engine must produce a lot of power to climb the mountain. However, less power is produced at high altitude due to low barometric pressure. This is the end of Lesson 2. Now, stop the tape, return to your workbook, and complete the progress check questions for this lesson. Please do not rewind the tape. Lesson 3, Electronic Engine Control. In the preceding lessons, you saw different conditions related to temperature, airflow, pressure, throttle opening, and engine speed. This lesson describes the devices used for measuring conditions and adjusting engine systems to correspond to the requirements under those conditions. The Electronic Engine Control, or EEC system, consists of a microcomputer, input sensors, output controls, and wiring. EEC systems rely on electrical and electronic devices and electrical circuits to do the job. A good understanding of basic electricity and magnetic force is necessary to comprehend this lesson. The computer makes decisions for the proper air-fuel ratio and ignition timing for each set of conditions. In an EEC control system, information about conditions is received by electrical signals from sensors. The sensors measure a condition and provide an electrical input signal to the computer. Sensors and computers can measure and analyze basic conditions, such as engine speed, temperature, and load. They can also measure and respond to other conditions, such as vibration and intake air density, oxygen content. EEC systems can fine-tune their adjustments by measuring the results. EEC systems can even diagnose their own circuits and devices, report malfunctions to the driver, and give information to help a technician locate the problem. Voltage can be used as a signal by changing levels or amplitude, changing waveform or shape, or changing the speed at which the signal switches from one level to another level or frequency. There are two kinds of voltage signals, analog and digital. Both of these are used in the computer system. It is important to understand the difference between them and the different ways they are used. Analog signals control information by regulating the current or voltage. Current or voltage can take on any value within the range of operation. Digital signals control information by switching the current or voltage on and off. An analog signal usually gives information about a condition that changes continuously over a certain range. For example, temperature information is usually provided by an analog signal. Digital signals are also variable, but not continuously. A digital voltage signal is limited to two voltage levels, positive voltage and no voltage, 0. The amount of positive voltage must be specified in the circuit design, for example, 5 volts. Any lower voltages would not be recognized. Significantly higher voltage would most likely damage the circuit. Digital signals are especially useful when the information can only refer to 2 conditions: yes, no, on, off, or high, low. A digital signal can be illustrated with a grounding switch sensor. With grounding switches, source voltage is applied through a load: motor, light, resistor. When the switch is open, there is no voltage drop through the load. Thus, the signal is full voltage. When the switch is closed, all the voltage is dropped through the load, and the signal goes to 0 voltage. There is no in between. The signal is either full voltage or 0 voltage. Therefore, the digital voltage signal has a square-shaped waveform. The wave is square because voltage does not build up and decrease gradually. Instead, it almost instantly goes from maximum to 0 to maximum to 0, and so on. The amount of on time is measured by the width of the voltage pulse. The percentage of the time that the voltage is on during one cycle is called the duty cycle. A longer duty cycle has an on-time pulse that is wider and an off-time pulse that is narrower. For example, a 34% duty cycle has a narrower on-time than a 66% duty cycle. The frequency of the pulses is measured in cycles per second. A higher frequency has more cycles per second. It is depicted in a graph or on an oscilloscope by more voltage spikes. To get more voltage spikes in the same picture, each one has to be narrower. However, the width of the voltage spikes does not affect the duty cycle, because the duty cycle is the percentage of on time in each cycle. The PCM measures pulse width for some inputs and also generates outputs with varying pulse widths. Input voltage can be either AC, alternating current, or DC, direct current. Both types are used in electronics. A steady DC voltage is drawn on a graph as a straight line. A steady AC voltage is drawn on a graph in a waveform called a sine wave. It has positive amplitude when current is flowing one way and an equal negative amplitude when it's flowing the other way. Generators can generate a very large amplitude, amount of voltage, while magnetic pickup sensors will generate only very small amplitudes. Both devices generate AC current. Signal inputs are electrical. They are conducted to the PCM with wires. Any opens, high resistance, or shorts to ground in the wires will cause the PCM to receive inaccurate information. For example, if an input of 2 volts means one condition and 1.5 volts means another, extra resistance causes the computer to respond to the wrong condition by changing the voltage signal, such as 2 volts to 1.5 volts. Similarly, if an input of 0 volts means one condition and 5 volts means another, then a short to ground or an open circuit causes the PCM to respond to the wrong condition. A switch uses a mechanical action to open or close a circuit. Switching may be done with either power side switching or ground side switching. Power side switching circuits are also called voltage input switching circuits. They carry voltage to the PCM. Source voltage is supplied by a circuit from another component or the battery. When the component is turned on, the power also flows to the PCM. The PCM provides the ground in this circuit. If the switch is not turned on, there is no voltage to the PCM. Ground side switching circuits receive a constant source of voltage from the PCM, typically 5 volts or 12 volts. The voltage from the PCM is called reference voltage. The sensor is an on-off switch that opens or closes the circuit between the sensor and the ground. The PCM senses the voltage drop by comparing sensor voltage to its reference voltage. An open switch causes a voltage drop across it. A potentiometer uses a variable resistor to regulate the voltage in a circuit. The resistance changes depending on the position of the wiper arm. A potentiometer is used to measure position throughout the range of travel of a device. The device moves the wiper arm in the potentiometer so a particular position of the component corresponds to a particular resistance. A thermistor is a variable resistor. The resistance changes with the temperature. Resistance decreases as temperature increases, so the voltage signal is lower at high temperatures. A transducer is a variable resistor that changes its resistance value as the pressure changes. Transducers are used to measure pressure. The Hall element generates a small voltage when it's exposed to a magnetic field, and the voltage stops when the magnetic field is removed. An optical device switches a ground circuit on and off electronically. The optical sensor consists of a light-emitting diode, LED, and a phototransistor. A phototransistor completes a circuit when it's exposed to light and opens the circuit when no light is applied to it. The optical sensor is attached to a fixed object, such as the bowl of the distributor. A disc with holes in it is attached to an object that rotates, such as the distributor shaft, and rotates with it. The disc passes through a slot in the sensor. The disc is in between the LED and the phototransistor. Light from an LED shines through a hole in the disc each time a hole is in front of the LED. The phototransistor detects the light shining through the hole. As the disc rotates, the light from the LED is alternately passed and blocked. Each time light is passed, the phototransistor completes a circuit until the light is blocked again. A variable reluctance device is a small AC current generator. It consists of a toothed ferromagnetic trigger wheel, or reluctor, permanent magnets, and a sensor coil. It works by rotating the reluctor through the magnetic field in the following manner. As a reluctor tooth approaches the magnetic field begins to distort. This distortion causes an induction of positive voltage in the sensor coil. As the tooth gets closer to the magnetic field is distorted more, so more positive voltage is induced. As the tooth gets very close to the magnetic field changes less, so less positive voltage is induced. When the reluctor tooth is aligned with the magnet, there is no distortion in the magnetic field, so no voltage is induced. As the reluctor tooth moves away from the magnetic field distorts in the opposite direction. This distortion causes an induction of negative voltage in the sensor coil. As the tooth gets farther from the magnetic field is distorted more, so more negative voltage is induced. As the tooth moves even farther away from the magnetic field is distorted less, so less negative voltage is induced. When the tooth gets far enough away, there is no distortion in the magnetic field, so no voltage is induced. The current produced has sine wave voltage pulses because positive and negative voltage of varying amplitude is produced. Faster rotation produces more pulses, which means that more voltage is induced. A variable reluctance sensor, or VRS, may be used in an EEC system to measure engine speed, RPM, or position of the crankshaft for cylinder identification, or CID. Different numbers of teeth on the trigger wheel can be used to measure crankshaft position and RPM. For example, the number of teeth can be equal to the number of cylinders, or the number of teeth can indicate a certain number of degrees of rotation of a shaft. For example, if a trigger wheel has 8 teeth, each time a tooth passes, the magnet signals that the shaft has rotated 45 degrees. The variable reluctance device may provide the signal to identify the position of cylinder number 1. For example, if the trigger wheel has teeth located at 10-degree increments, you would expect it to have 36 teeth. However, if one tooth is removed, when the part of the trigger wheel with the missing tooth passes the sensor, there is an unusually long time span between pulses. The ICM recognizes this to identify the location of cylinder number 1. In this case, the VRS provides RPM, crankshaft position, and CID. The frequency generator pressure sensor is unique because the frequency of its signal varies. It's used to measure pressure in the air. Piezoelectric devices are used to measure vibration. A piezoelectric device generates a voltage spike as pressure is applied. Each time pressure is applied, another voltage spike is generated. So more vibration will produce more voltage. The voltage amplitude is higher if the vibration pressure is stronger. An oxygen sensor, or O2S, is used in an EEC system to measure the presence of oxygen in the exhaust gases. There are two basic types, zirconium and titanium. A zirconium-type oxygen sensor is a signal-generating sensor. A zirconium oxygen sensor generates voltage by the chemical reaction between two dissimilar materials, just like a battery. Part of the sensor is exposed to outside air, which contains a lot of oxygen. The tip of the sensor is exposed to exhaust gases, which contain much less oxygen. When the sensor is heated by the exhaust gases, voltage is generated by the difference between the oxygen content at the sensor tip and the oxygen content of the outside air. A hot wire device is used to measure the amount of air flowing over itself. The hot wire device receives two voltage inputs. It receives battery voltage, which is used to heat a resistance wire or hot wire heating element. A thermistor regulates the current to keep the heating element at a constant temperature. Air flowing over the heating element cools it. The thermistor adjusts the current flow so that the heating element remains at the same temperature, regardless of how much air is flowing. Colder air would have the same effect as higher airflow. To compensate for air temperature differences, the hot wire device has another circuit to measure ambient air temperature. This is called the cold wire, and it has a thermistor to vary the current through it according to the air temperature. The two thermistors act together to determine total resistance. A hot wire device regulates signal voltage to the PCM. Resistance in the signal circuit is adjusted according to the thermistors for the hot and cold wires. The PCM reads the signal voltage to determine how much air is flowing. The PCM takes the information about conditions from the input sensors and looks up the right output from its program. All outputs from the PCM control DC voltage. Most of the output devices have battery power to them, and the PCM controls each device's ground circuit. These are the devices that electric outputs can operate: the malfunction indicator light, or MIL, solenoids, relays, modules, and motors. The computer has the ability to diagnose itself and the circuits for input sensors and output devices. The PCM recognizes electrical problems in some circuits. It monitors the inputs from sensors and recognizes abnormal inputs. It also recognizes abnormal responses to outputs. Diagnostic capabilities vary depending on the particular EEC system in the vehicle. EEC 5 is the second generation of onboard diagnostic, or OBD, systems, called OBD2. OBD is required by the government to monitor systems that could cause the vehicle to exceed exhaust emission limits and store a diagnostic trouble code and illuminate the MIL. EEC 5 provides a data storage stream and freeze-frame data which describes engine conditions at the point when the first malfunction is detected. The program requires a drive cycle, or trip, before storing certain malfunctions, since certain events only occur when the vehicle is driven in a certain manner. This is the end of Lesson 3. Now stop the tape, return to your workbook, and complete the progress check questions for this lesson. Please do not rewind the tape. Lesson 4. Base engine causes of drivability symptoms. This lesson describes the drivability symptoms that can be caused by the base engine. Drivability symptoms will occur if any of the requirements for good combustion are not met. One of those requirements is compression. Compression is dependent upon the cylinder to bring in a normal amount of air-fuel mixture and containing that air-fuel mixture in the cylinder. These operations are the function of the base engine. There are other malfunctions of the base engine that can simulate drivability symptoms. This lesson provides an overview of drivability symptoms and possible causes related to the base engine. An engine repair course would help you understand the relationships between drivability symptoms and the base engine. Low engine compression means that the compression pressure in all of the cylinders is uniform but abnormally low. Low engine compression can cause drivability symptoms like lack of power, poor fuel economy, engine stalls, hard starting or no start in severe cases, excessive emissions, and exhaust smoke. High engine compression means that the compression pressure in all of the cylinders is uniform but abnormally high. High engine compression can cause drivability symptoms such as spark knock and hard starting. These symptoms and their relationship to cylinder pressure will be explained in the ignition course of the engine performance curriculum. Uneven compression means that there is a significant difference in the compression pressure in one or more cylinders. Different compression pressure in individual cylinders causes unbalanced power delivery. Differences in power produced by each cylinder can cause drivability symptoms such as engine runs rough and engine misses. In addition, the drivability symptoms listed for low engine compression and high engine compression are caused when one or more cylinders have abnormal compression pressure. Low compression pressure in one or more or all cylinders can be caused by valve trains restricting or preventing normal airflow because the valves do not open their normal amount due to worn camshaft lobes, bent push rods, inoperable hydraulic valve lifters, or any of these parts not to specifications. Low compression pressure can also be caused by valve trains restricting or preventing normal airflow because the valves do not open their normal amount due to a slipped or improperly installed timing belt or chain. In this case, compression pressure will be low in all cylinders. Any cylinder that produces less power will be assigned a number less than 100% depending on its power relative to the highest one. A power balance test will not distinguish whether the power in a cylinder is low because of compression, ignition, or air fuel. However, it will identify the particular cylinder or cylinders to investigate. This is the end of Lesson 4. Please stop the tape, return to your workbook, and complete the progress check questions for this lesson. Do not rewind the tape. Lesson 5, Non-Engine Causes of Drivability Symptoms. This is an overview of the powertrain and other systems of the vehicle that may cause drivability symptoms. Other courses are available which include greater detail on the operation and diagnosis of these systems. This course covers these topics for the purpose of making you aware of the relationship between drivability symptoms and possible causes. Accessories are driven by the engine through belts and pulleys. These accessories include the power steering pump, secondary air pump, generator, water pump, and air conditioning. An unbalanced condition in any of the pulleys or belt-driven accessories could cause a vibration that may simulate a rough-running engine. Causes of imbalance include bent pulleys, gouged belts, and bad bearings. An imbalance is also caused by separation of the rubber insulator in the harmonic balancer at the... A harmonic balancer is used on some engines to absorb natural vibrations. Automatic speed control systems control the throttle opening to maintain a constant speed when they're engaged. During hill climbing, they will open the throttle as far as necessary to produce the amount of power needed. This control will change the speed of the engine. A malfunctioning speed control can make erratic or abrupt changes to throttle position. A malfunctioning speed control may disengage without warning, which causes the throttle to close suddenly. Also, the speed control may kick out under heavy loads. The automatic transmission will shift and operate the torque converter lockup clutch as normal during use of the speed control. With the speed control operating, the driver may not realize the changes in accelerator position, so the shift may not be expected. This video was intended to provide you with a basic understanding of the essentials of drivability diagnosis. Remember, procedures and specifications are subject to change without notice. Always consult the latest available information. This is the end of Lesson 5. Please rewind the tape, then return to your workbook and complete the progress check questions for this lesson.